Thanks for coming to our Biogeochemistry Science Friday. Our first talk today is by Jiafu Mao. Go ahead, Jiafu.
Thank you, Forrest. Thank you, everybody. So, yeah, I'm going to present the development, evaluation, and application of new soil moisture products. So, relevant dataset paper was just published at the ESSD. And the paper on the detection and attribution of long-term changes of soil moisture-based drought is still under review. So I would appreciate the excellent contribution to these studies from my co-authors, especially Dr. Yaoping Wang from the University of Tennessee at Knoxville, and the funding support mainly from the Rubisco project. So you all know the importance of soil moisture on the droughts, water energy momentum balances between the land and atmosphere, and the ecological systems, including plant photosynthesis and phenology, wildfire dynamics, soil microbial activities that affect carbon and the nutrient cycling. So the development of high quality global soil moisture datasets benefits many applications, such as understanding drought changes and ecosystem dynamics, studying land atmosphere feedbacks, benchmarking model capabilities, and initializing weather and climate forecast systems. So the majority of soil moisture products fall into 5 categories, including in situ observations, satellite observations, offline land surface model simulations, reanalysis, and Earth system model simulations. So in situ measurements provide the most direct soil moisture observations at the pond scale, but are too sparse to be interpreted to the global level. Satellite-derived soil moisture product records, as you know, only penetrate the top few centimeters of soil and contain errors and spatial gaps, typically caused by factors such as a change in path, dense vegetation, frozen soil, water bodies, and radio frequency interference. So the soil moisture in those model outputs, like land surface model, reanalysis, and Earth system model simulation, so they usually span multiple soil layers and have no spatial and temporal gaps, which is convenient for regional and global analysis. However, model simulations may contain considerable errors because of inadequacies in the model physics, parameterization, and the drivers. So theoretically, merging multiple source datasets would overcome the limitations of individual datasets, resulting in long-term global gap-free multi-layer soil moisture products for research purposes. So there is active development toward generating more accurate gap-free soil moisture datasets. Methods for filling the spatial gaps in satellite observations have been under investigation, but the resulting estimates either cover short time periods or target only parts of the globe. One global multi-layer soil moisture product was generated by upscaling in situ observations using machine learning and selected soil moisture predictors. However, this work only focused on the period from 2000 to 2019. Unlike current global reanalysis that directly assimilate satellite, some studies merged in situ observations, or both in situ and the satellite observations with offline land surface models to improve accuracy while retaining complete spatial temporal coverage. Nevertheless, these efforts are mainly conducted on the regional scale using limited sets of land surface models. So therefore, the need exists to develop global merged soil moisture products that comprehensively combine the information from the latest in situ and satellite observations, offline land surface models, reanalysis, and Earth system models using advanced fusion methods here, including the unweighted averaging, optimal linear combination, and the emergent constraint method. So for this work, 7 new monthly multi-layer soil moisture datasets at half-degree resolution for the 1970 to 2016 were produced by implementing these merging algorithms onto different combinations of the above-mentioned raw soil moisture estimates. So the merged soil moisture products were evaluated against the reserved 40% in situ observations, as well as a few graded reanalysis satellite and machine learning upscaled soil moisture dataset. Although the merging process aimed to use as many existing soil moisture datasets as possible, the graded datasets in this table were not used in the merging because of incompatible vertical resolution, non-global spatial coverage, or short temporal coverage. So such evaluation against the multi-source graded datasets complements the evaluation against the in situ observations by providing sanity checks on the behavior of the merged products at large scales. So for the performance of the merged soil moisture products against site evaluations, so for those evaluation against the validation set of these ISMA soil moisture observations, so the merged products here denoted using different colored shapes, they generally show the smaller magnitude of bias, smaller RMSE, and a higher correlation than their source datasets, denoted using the boxes here, from which the products were merged. So the bias of both the source and the merged datasets shifted from mostly positive to mostly negative from the shallowest to the deepest soil layer, indicating a tendency toward the overestimation of vertical soil moisture gradient. Then the shallower soil layers also tended to have lower MSE, higher correlation than the deeper layers, and the bias values of individual merged products were generally similar. So these figures show the global evaluation results in terms of climatology, seasonality, trend, and anomalies. So the evaluating results for the merged soil moisture products against independent or semi-independent graded soil moisture datasets were highly dependent on the evaluation dataset. So the asterisk indicates that the magnitude of the bias, RMSE, or correlation of the merged products here, those merged products, is better than the product's source data sets here in the same column. So within each column of each panel of this figure, the merged products generally had lower MSE and higher correlation than the average RMSE and the correlation of corresponding source data sets. And those land-surface model reanalysis satellite dataset based products, those ORS-based products, so they generally had a lower MSE and a higher correlation than those CMIP5 or CMIP6 model-based products. So because all the merging procedures essentially involve averaging over multiple source data sets, the variability and the trends of the merged product may be damped compared with the source data set because of mutual cancellation. So to examine whether this is the case, power spectral densities were calculated on regionally averaged time series of the merged products and the source data sets. So the power spectral densities of the mean, those offline land-surface model reanalysis satellite, those ORS, OLC ORS, or EC ORS, so method-based product, so they very rarely exceeded the boundaries of their source data sets, showing that at least at a regional level, these merged products did not underestimate the temporal variability in soil moisture. So for the evaluation against selected drought events. So lower values in the SCPDSI and soil moisture anomalies in these figures are indicative of drier conditions, and higher values here indicate wetter conditions. So for the United States 1985 to 1992 drought, the SCPDSI showed a gradual expansion of drought from 1985 to 1988, and a gradual elevation from 1989 to 1992, with the most severe drought being reached in the Northern Great Plain in 1988. So similar evaluation patterns can be also seen for different 0 to 10 centimeter soil moisture anomalies for different products. So these figures show the annual partial correlations of soil moisture with precipitation, temperature, and shortwave radiation, and the spatial distribution of dominant driving factors for individual merged soil moisture products. So based on partial correlation, precipitation was found to dominate the soil moisture variability in different products over the most of the globe, and generally had significant positive partial correlations. In all the merged products, air temperature had significant negative partial correlations with soil moisture in many continents, especially in Southwestern United States, Eastern South America, South Africa, and the Mediterranean. So the primary negative correlations were consistent with the physical expectation that higher temperatures induce higher evaporative demand and thus lower soil moisture. However, downwelling shortwave radiation was rarely shown to be a dominant control of soil moisture variability for different merged products. Then based on this developed soil moisture datasets, we have tried different applications. The first one was about the quantification of human contribution to soil moisture-based droughts. So we calculated a standardized soil moisture index, which is SSI, for two soil layers, which are 0 to 10 centimeter and 0 to 100 centimeter from this newly merged soil moisture dataset, and applied a formal detection and attribution analysis to quantify the impacts of natural and anthropogenic fallings on the monthly trends in the zonally averaged standardized soil moisture index. So these figures show example signals of the pulsatile observation denoted using black line. The shapes and 95% CIs of the Gaussian distribution fitted to the signals of CMIP6 simulations under different forcing, like the all simulations, anthropogenic only simulation, greenhouse gas only simulation, the combined GHG aerosol, natural forcing only simulation, aerosol only simulation, and the 95 and the 99 CIs of natural internal variability, which is noise. All the signals were for the 1971 to 2016, and the noises were for the window length of 46 years. For example, based on the all fingerprint here, for the surface soil layer, the signals of the pulsatile observation were detected at 99% confidence level in September to November. Then the detected signals of the pulsatile observation were within the 95% CIs of the all ANT, GHG, AER, and the GHG signals, but outside the 95 CIs of the NAT, ANT, and the aerosol signals. Therefore, the GHG forcing alone, or in combination with other anthropogenic or natural forcings, can explain the significance of the signals of the pulsatile observation. But the NAT or aerosol forcing alone cannot. So our findings highlight the predominant human contribution to the spatial temporal heterogeneity of aridification and provide a comprehensive basis for drought risk reduction strategies and activities. Relevant manuscript is still under review. So the second one is about the application of the merged soil moisture datasets onto the ILAM hydrology benchmarking. So as you all know, ILAM evaluates model simulated carbon hydrology radiation and energy cycle, and different response relationships using various sources of observation. However, for the hydrology component, the current version mainly includes the global or regional evaluations of evapotranspiration, runoff, and the total water storage, but is unable to systematically conduct soil moisture evaluations. So for this work, we did some initial applications of these products onto the ILAM hydrology benchmarking. So this just show the results from the merged product climate tolerable means of the merged products for these two soil layers and the results from this BCC model. I'm also going to show some other results. Let me click this link. Can you see my screen here? Sorry, can you see my screen?
Yep, application 2, ILAM SM benchmarking.
Oh, I mean the website. So
no, we don't see the website.
You might want to exit your presenting mode first, then we can see
okay.
your website.
Stop sharing. I mean, sorry about that. Try again. Screen.
You might be in your another screen. Yeah.
Okay, so you can see now. Yeah, this just shows some quick examples on, I mean, the results we have for the ILM development for the soil moisture part. So this here, so it's the, yeah, we have 3 models here, but from the overall scores, you can see generally the BCC model has the highest overall score. Then the model from CAN ESM and CSM, they have relatively lower scores. Then those results, then let me go show some other examples here for the all models, for example. Yeah, this show this climate tolerable mean results from for 4 different soil layers for the benchmark data sets. Then for these results from different models. Then we also have the results for the timing, the max months, the benchmark results and the different models. Then for some score, for example, for the phase score, you can see this here. Yeah, for the phase score, yeah, interestingly for the CAN ESM and the CSM, so their score looks quite close. So, but the PCC model generally their score for the especially for the surface soil layer, you can see, yeah, and maybe have more area that shows higher scores. Then we also have this time series, this spatial integrated regional mean. Yeah, this time series, the black line are the observations. For example, for the first layer soil moisture, yeah, here you can see the CAN ESM maybe just in terms of magnitude, it's quite close to the newly merged soil products. But for example, for CSM model here, compared to the benchmarking data sets, it generally shows overestimated soil moistures for different soil layers. And then for others, yeah, we also have the relationship scores. For example, the relationships between soil moisture and the evapotranspiration for different models. And this actually might be, yeah, this one. So again, yeah, talking about the response or relationship between soil moisture and evapotranspiration. So yeah, for the CAN ESM again, found these first, second soil layers. So they generally show quite closer response relationships to the benchmarking data set. Those just some initial applications. So yeah, we are still working on the new developments in terms of we are going to add those sensitivity benchmark, like the sensitivity of the soil moisture to those precipitation, temperature, radiation, and also these trends related benchmarking, benchmark or metrics. Let me stop sharing this. And, so, okay. So just a summary of these results. So this study achieved the goal of creating long-term gap-free multi-layer soil moisture products for the 1970 to 2016 period at global half-degree, monthly, and for four different soil layers, and it can be downloaded at this website. So overall, the merged soil moisture products showed better performances than their source data sets, temporal homogeneity, and the ability to capture large-scale drought events and a reasonable climatic response characteristics across the globe and multiple soil layers. The ranges of performance metrics of the new datasets against the in-situ measurements and semi-independent graded soil moisture estimates were broadly within the estimates reported by previous soil moisture evaluations, although making a strict comparison is difficult because of the widely different spatial temporal coverage and resolutions. So 3 new soil moisture products developed from the satellite observations, reanalysis, and offline landscape models were shown to perform better than those based on the Earth system models. So therefore, they are recommended here for future applications, such as the detection and attribution of historical changes of soil moisture and associated extreme events, providing the initial and boundary conditions for atmospheric models, benchmarking various types of models, and managing drought and flood risks. So for next steps, so we plan to analyze the impacts of long-term soil moisture changes on above and below ground carbon dynamics, like those greening, browning, or wildfire soil moisture relationships, those type of scientific questions, and provide initial and boundary conditions for atmospheric models like the DOE E3SM, NOAA ESM4, and NSF CSM, etc. So for the data development, we will assemble more in situ soil moisture data sets like those from DOE NGs, American Flux, NEON, etc., and implement other advanced fusion methods, including the extended co-location, machine learning, etc., to contribute to the new eco-hydrology working group we are actually proposing for the next phase of the RUBISIC project. We would leverage existing RUBISIC working groups like the American Flux, the soil the soil carbon working group, and perform new data set synthesis and model data integration. So we will also understand and benchmark the global hydrology dynamics using multi-source data sets and various benchmarking methods, especially the functional relationship benchmarks. So finally, we would like to find new ways to use these benchmarking results to improve model parameterization, predictions, and projections. For example, we could apply different evaluation metrics to constrain ensemble Earth system model projections and forecast using novel statistical and machine learning techniques. Thank you. I think that's all.